Hello everyone, welcome back. I hope you guys are doing well. Here's myself Satvik, and here's my technical seminar topic: Neuromorphic Computing Chips that think like humans, under the guidance of Ms. Santya R, the Assistant Professor of ISC. Let's begin. Here's the content paths: introduction, related background, working implementation, applications, literature survey, conclusion, and references. Here's the introduction part. Neuromorphic computing is an interdisciplinary innovation combining neuroscience, computer science, and electronics to create chips that mimic human brain structure and function. Traditional computers use the von Neumann architecture where the CPU and the memory are separate. This leads to a latency and energy inefficiency known as the von Neumann bottleneck. So neuromorphic chips in contrast use brains-like architectures that integrate memory and processing, allowing for real-time response and significantly low energy usage. This paradigm shift in computing is particularly impactful on AI tasks like patterns recognition, decision making, and sensory data processing. Neuromorphic systems use spiking neural networks where information is transmitted via timed electrical pulses, so similar to how neurons communicate biologically. Next comes the related background, where traditional digital computing has dominated for decades, but its limitations are becoming more apparent with AI's growing computational demands. One major hurdle is von Neumann bottleneck, which separates memory and processing units, leading to excessive energy consumption and latency. Neuromorphic computing, on the other hand, is modeled after biological brain. Massively parallel and distributed structure, the brain processes sensory inputs efficiency using roughly 20 watts, a stark contrast to supercomputers requiring megawatts. So here's the key biological inspirations: basic units that fire signals as the neurons, and again the synapses in human biological system are similar to this, connections that adjust strength based on experience. Spiking communication, brain uses spikes, not continuous signals, leading to event based processing. Next comes the working and implementation part. Neuromorphic chips consist of arrays of neuron like processing elements, so interconnected via synapses like communication links. Each neuron operates independently and asynchronously, enabling event driven computation. Key components include a neuron core, processes include input spikes and generates output, and stores weight that influence spike transmission. Route spikes across the chip via address event representation, whereas the communication fabric. Next comes the working continued version of working part. The system processes only when spikes occur, drastically cutting down idle energy use. Unlike CPUs and GPUs, neuromorphic systems are non-von Neumann, meaning computation and memory are co-located, enabling faster and more localized data processing. Design varies between analog and digital, so implementations, chips like Intel Lohi even feature plastic synapses capable of local learning without external control. This brain-inspired architecture enables scalable, fault-tolerant, and ultra-low power operation, ideal for real-time AI at the edge. Here's the flowchart of how it works. Once you start by prompting, the chip gets into the sensory input, a real-world data where visual, auditory, and tactile input are three different things to focus. But after getting the things, it gets into signal encoding where sensory fusion works. It converts the analog signals into spikes, like spikes encoding tech in them. Then comes the SNNs, spiking neural networks, where real-time AI has been used for it. And once after that, synaptic weight modulation, it's been extracted from cloud offloading, weight adjusted via spike terms, and learning from repeated patterns. Then comes the neuromorphic hardware execution, and chips like Lohi and Rohnath, SPINR, and ultra low power parallel processing. Again, it's used by the real time AI. Mm. Next comes the output layer. After getting all things, again the learning updated based feedback, again it's a different thing. Once after that, it gets into the loop of feedback, and it's purely optional to an individual's training. After that, it's an end of the real world explanation of the result of whatever the prompt has been given by an individual. And here's the application and future enhancement. Neuromorphic computing has broad applications. The robotics part enables adaptive, low power control of motors and real time decisions, and decision making. Sensory processing, again, the vision, auditory processing, and olfactory modeling. When it comes to healthcare, used in brain machine interfaces for prosthetics and neurological therapies. After that, it's in edge AI, efficiency for battery operated IoT devices requiring fast local interference. After that is the security, where used in anomaly detection for cyber physical systems. And with the brain like efficiency, neuromorphic systems outperform traditional AI and scenarios that demand speed, adaptability, and power consciousness. Well, all these things we have been building a model or similarly like a human thinking system. So we are designing the chips, neuromorphic chip is basically how human, it's a mimicking of human tendency. Again, it's trained by humans to get similar results. Next comes the application, the continuous version. Here's the future enhancement. Standard toolkits like Lava and NextDF and the Brain2 are maturing, and 3D integration for higher synaptic density and the lower latency. Next comes the hybrid systems, combining neuromorphic cores with the traditional CPUs and GPUs, and quantum neuromorphic chips, next generation hybrid processors. Again, the neuro-inspired algorithms, spiking neural networks for unsupervised and continual learning. The future lies in the synergy between the biological learning and the silicon speed. Here's the literature survey. D. Kuzum S. Basically, all these are Japanese authors, and 2023 is the year of publication. The study explores brain-inspired synaptic electronics using emerging memory devices like ReRAM and PCM. PCM is basically a phase change memory. It emphasizes how these technologies mimic synaptic plasticity in real time for low power neuromorphic systems. After that is a 2022 paper, where this paper analyzes spiking neural networks and their hardware accelerators. It highlights advances in event driven processing and energy efficiency, focusing on neuromorphic chips optimized for real world AI tasks. Again, the 2022 next paper comes, where it investigates in memory computing for neuromorphic tasks. The paper outlines how phase change memory helps integrate processing and storage, reducing latency and enhancing parallel processing capabilities. The other two comes with the 2023, where discusses the next generation neuromorphic hardware based on non-volatile memory. It details progress in device miniaturization and endurance, so showing promise for real-time learning on edge devices. Introduces a hybrid architecture combining CMOS and memristive devices for neuromorphic computation, where the system shows improved learning accuracy and it's suitable for robotic sensory processing applications. Conclusion: neuromorphic computing represents a transformative leap in artificial intelligence. By mimicking the brain structure and learning behavior, these chips offer unmatched energy efficiency, adaptability, and responsiveness. While the technology is still evolving, its applications from robotics to healthcare are already reshaping what's possible with intelligent machines. As we overcome current limitations, neuromorphic systems will become the backbone of next generation AI, especially for real time, power sensitive applications. It brings us closer to building truly intelligent machines, not just with a fast computation but with a real world cognition. Here's few reference part, where it helped me in doing this presentation, and moreover I chose the sample IEEE paper for this. We can go through this. Thank you guys.